Hi everyone, we are talking about the stable market problem from this month's Codechef challenge, and this video has taken a long time to come out, so thanks for waiting. We have an array given to us and we have to find blocks in that array. Okay, so the way you define a block is a set of contiguous values which are equal. So a subarray in that array which has all elements equal is a block, right? And so blocks are of different sizes, like this block is of size 1, which has values of 2. This block is of size 3, values of 10. This block is of size 2, and this block is of size 1. So our job is to answer queries, Q queries, such that you're given a range from left to right for each query, and you're given a number k. So you have to find all blocks in this range which have size greater than or equal to k. So that's our job, simply put. Now, there are many solutions to this. Because of the time complexity requirement, I really like this question because this actually allowed you to think in terms of not which data structure should I apply, but what logic do I need to apply. So what you need here is range queries. Right? And because this question is so general, you can apply almost any range query technique to this problem. So quickly discussing a few of the approaches, segment trees can be applied. Very similar to how you apply segment trees is the square root decomposition technique. The third thing you could do is use Moore's algorithm, which is as suggested in the editorial called offline query. And fourthly is binary search. Alright, the most efficient approach is using binary search. So that's what we'll be talking about. These three approaches, they require some prerequisite to understand. Of course, binary search also requires some prerequisite. You need to know about binary search. But segment trees is discussed in a different video, square root decomposition also, and we have also discussed Moore's algorithm, in fact, quite a bit in detail. So if you want to have a look at those videos, you can. But we are going to be talking about the binary search approach. A very quick note on segment trees or square root decomposition, if you're using a data structure to handle the ranges, is that you'll have particular block sizes. So in segment trees, you have hierarchical block sizes, while in square root decomposition, you have fixed block sizes. So let's say this is your block, and this is your other block, which you have. Now, every time that you're actually jumping over blocks, you need to make sure that you're not getting rid of, this edge case. So let's say I have 7 occurring 3 times here. And at the very start of this also, I have 7 occurring 2 times here. So essentially I have a block of size 5 at this point. This entire thing was a block. And if a query comes in for k equal to 4 or 5, then I should reply with one block of 7s also. Okay, so this is an edge case, and there are quite a few edge cases that you need to think of when you are using a data structure here. Moore's algorithm will work quite nicely, I think. Yeah, it will work quite nicely, but we are going to be discussing binary search because we haven't. So let's have a look at that. Before we can start off with the solution, we need some extra information. Okay, so what we need is an array which is going to tell you the block indexes, the index of the elements within their respective blocks. So 1 and 1 have indexes 1 and 2. And 12, 12, 12 have indexes 1, 2, 3. So these are giving you the indexes of 12 within that particular block. So you can see this array having been constructed. So the very first element of that array is going to be initialized to 1 because the first element will have index value 1. And after that you check if the current value is the same as the previous value from 1 to n minus 1. If that's the case, then you assign plus 1 of whatever the previous value was to the current block index. Otherwise, you start off with a new block, and that's equal to 1, starting off new block. With this array, we can answer our range queries very efficiently. Imagine that you haven't been given any range queries yet, and what you're doing is, someone asks you, find me all the blocks having size greater than or equal to 2. Alright, so that is block of 1s, block of 12s, and block of 20s. Yeah. So 3 blocks, 1, 2, and 3. And this makes logical sense. Just by looking at the number of times that 2 occurs in block B, we can tell how many times such blocks greater than or equal to 2 occur in the original array. The reason being that, if 2 occurs, it means that a block reached the index 2. Means that the block has to be either greater than or equal to 2. That's the only time it can reach that particular index. So yeah, this makes sense. But there is a small problem with the range queries part. If you imagine a range query perfectly falling within blocks, this range query is perfectly falling within these blocks of 12, 18 and 20, then it's perfect. Life is simple. You just return the answer of the number of times that 2 occurs in this range. Okay, we'll see how to answer that efficiently, but we need to just answer the number of times 2 occurs in this range. If, however, your rightmost block does not entirely fall within the range, let's say it's somewhere over here, right? Even now things are simple. You just need to answer the number of times 2 occurs in the given range. Why doesn't the rightmost block affect it? Because the rightmost block could not reach up to 2. So because it couldn't reach up to 2, meaning that it does not have a block of size greater than or equal to 2. If it couldn't reach up to 2, means it doesn't have a block of size equal to 2. Forget greater than 2. Okay, so the rightmost block was moving forward, couldn't get to the point that you want. Therefore, this query still holds. So the 3 scenarios, just note that down. One is all blocks in range. That's one scenario. The second scenario is rightmost block not in range. That's also fine. We have just seen that that's perfectly fine. The third scenario is a little tricky when your leftmost block, and why did I say leftmost and not the left 5, 6 blocks? Because yeah, everything else is completely within the range. So the leftmost block is not in range. When this occurs, so something like this, it's partially in range. Okay, so when the leftmost block is not entirely in range, you need to consider a few things. Does 2 occur because of it in your subarray? If it does, then just remove it. Blindly remove the contribution of the leftmost block which is not in range. Okay, if the 2 occurs. If 2 doesn't occur, if let's say this array was of size 3, 1, 2 and 3, and then 3 would be here, then keep it that way. And then we need to look at some edge cases now. And in the code here, we have block objects, which mean you have a particular block and it has start and size as the 2 parameters in it. So this is trivial to do because when you're running, when you're making a linear scan to create the array B, you can go on creating the blocks also. Such that whenever you're creating the new block, like when we are setting it to 1, you can create a new block that time of size 1 and left index equal to whatever index you were on I. And if you're not doing that, then all you need to do is whatever block you have current, you're going to set that to block.size plus plus. Okay, simple operations to perform. The only edge case that we are looking at is at the leftmost block creating issues, and so this block is the leftmost block, okay, in the code. Now block.start, if that is not equal to our index, our range left, then of course we need to come in, otherwise we wouldn't need to. Otherwise we would perfectly be in range. So if B of L, which means our range start B, is less than or equal to K, that means our block could not reach up to K at this point, but the block size is greater than or equal to K. That means our block will reach K, but at this given point it couldn't reach K. So for example, let's say K is equal to 2 or K is equal to 3 rather, yeah. And left is over here, L, capital L. So B of L is 2. this block is of size 3, so block dot size is 3 and block dot start is equal to the index of this, so that is 0, 1, 2, 3, 4. Yeah, 4. Okay, and L is equal to 4 again. In fact, no, block dot start is 3. So block starts from this index 3. Okay, so these are the things that we have, and now our program goes like this. If the left block index, if the index at L for capital B is less than or equal to K, so that is less than or equal to K because K is 3. So this condition satisfies, and the block size is greater than or equal to K. So the block size is equal to 3, which is greater than or equal to K. So this condition also satisfies. Then we should decrement whatever answer we had earlier. So we counted the number of 3's in this range. Let's say this is the range R up to R. So 3 would have been counted once. We should decrement it. Why? Because what I'm doing is finding out all the 3's which are without contention definitely in the answer. I'm keeping them. And for the leftmost block, I'm finding if there is any 3 being contributed, kick it out. We'll have a look whether it should be contributed or not later on. First, kick it out. So this is the only scenario when it will be actually counted, when you haven't reached K but you are going to reach K. So yeah, that's the only time that you're actually going to count it. So I am going to remove that contribution over here. Okay, take your time to understand this because this is the only edge case. Now comes the block size minus, what is this? Left index minus the block start. This gives you the number of elements which are being skipped in this block. Left index is over here, block start is over here. One element has been skipped in this block, in the leftmost block that we have right now. So the number of elements that you have skipped when subtracted from the size of the block, which is 3 here. Total size of the block minus the number of elements you have skipped. If that is equal to or greater than K, so if this part is greater than or equal to K, then we should increment the answer. The reason this makes sense is of course because do you have enough elements remaining after you have taken out the number of elements you have skipped? So if you do, then yes, you should increment the answer, otherwise you should not. And we have taken out all edge cases of what if it was already incremented by kicking it out. Yeah, so that's it. That's just this much part of the code for finding out the answer. A few things you need to take care of is how did we find the leftmost block in the given range? In the worst case, we could have gone on passing in a linear scan, and that would be order n operations. So for Q queries, order n is going to fail. We don't want that TLE. So what we are going to do is do this using binary search in just log n time. Okay. So finding the leftmost block is very easy because we talked about how we are going to be constructing the blocks and setting their sizes. We are going from left to right. So when we are constructing them, we are actually sorting them according to the leftmost indexes also automatically. Now, when we are given a range L to R, all we need to do is find if there is any block with starting index equal to left. Okay, if this is the case, then we don't need to do anything because all blocks are perfectly falling in the range that we have. If not, then we need to find the leftmost block. So the leftmost block can be found out by doing a binary search on this. We have already done that. So the binary search will definitely stop somewhere. Okay, and one of the properties of binary search is that it tells you where the key should have been. If you have an array of 3, 8, 4, 7, no, this is not sorted, so I'll call it 3, 3, 4, 9, 12. And if I binary search with value 5, then it's going to fall over here. Okay, it's called the insertion point. So the binary search always stops at the insertion point. You can tell what the insertion point is by doing a binary search. So if you can tell what is the insertion point, you can also tell which block start is close to L. So the leftmost block having an index less than L will be one away from the insertion point, which would be this very index over here. I'll take an example here to make things simpler. Let's say this is the array that we are searching on. Like we said, the key is equal to 5. Key is equal to 5. Binary search, we come to the middle, which is index 2. We see that 4 is less than 5, so we get rid of all elements from 4. Okay, these are taken care of. 7, 9, and 12, we again do the binary search here. Coming to 4, we see that 9 is greater than 5. So we get rid of these elements. We get rid of these elements, the ones which are greater. Right, job done. Now we just have one element. We come here, we see that, oh, it's not it. It's not equal to our element 5. So, and we have run out of space now. So this is the insertion point, 7. If you had a 5, then this is where it would be. Okay, but instead you have a 7 at that position. So normally what we do is we return the negative of whatever index we are at. It's -3. One of the things, like in Java, you can't return just the negative that because insertion point might be 0. So if you return the negative 0, that's equal to 0, and then people might think, oh, the element does exist at 0. So you don't want that. What you do is you do minus of whatever index you have plus 1. Okay, so even at 0, you get a -1. So that's the way it handles it. You just need to look at the documentation of binary search in your specific language, and you can tell what is the insertion point. But the usefulness of the insertion point is that you can now find the leftmost block, because capital L is what you're searching for. Capital L does not exist in your array. You did find where it should have existed in your array, alright? So that element over here, that is the element that you need to pick up, because that is the leftmost block that you're partially touching. Right? Take your time to understand this. The leftmost block that you're partially touching is the one at the insertion point. Okay. So yeah, you have your leftmost block. Now the algorithm is very simple, except for one small thing. Counting the number of k's in this array, in a sub-array, counting the number of k's in the range left to right, this is a problem because left to right can be as large as n. So few queries, again, order n, complexity, not going to work. We need some way to actually answer queries also efficiently. So let's do that. So what we are now doing is taking each value in the array B and storing the indexes at which it occurs in. Right, so 1 occurs at 0, 2, 3, 6, 7. 0, 2, 3, 6, 7. Yeah. 2 occurs at 1, 4, 8. 1, 4. Yeah, it must be correct. So what we need to do is store the indexes, but make sure that you don't hit n square complexity, space complexity, because you're taking every value and you're storing at most n elements. So don't go and construct the array like this, new int n cross n is too big. What we need is order n, because that's the space requirement for this actually, because these indexes occur just once and you're taking for all indexes. So that's fine. One of the ideas for this to reduce the space complexity is first construct a list. Once the list is constructed, convert that into an array. Order an operation overall, fine. You will get these indexes. So amongst these indexes, you need to do a binary search. Why? Because when you're given a range from left to right and a value k, you need to find the number of times that k occurs in this range left to right. And for that, you need to go to that particular index array, let's say 2. So 2 occurs at 1, 4, 8. Now, let's say the range of left is 3 to 9. Alright, so what you should be counting is 4 to 8 as your count, as your answer. This won't be the end of it though. We have already talked about how to deal with the leftmost block after getting this particular answer. Okay, so after that comes the process of dealing with the leftmost block. But yeah, first you need the answer, right? To be able to say how many 2's occur in this given range. So the number of 2's that occur would be doing a binary search on 3. So key is equal to 3. Let's do a binary search here. We don't know what the answer is yet, so that's here. So binary search here, indexes of 0, 1, 2. Go to the middle, you see 4. Is 4 greater than 3? Yes. So all elements from 4 to 8 are kicked out. These elements are kicked out, and you'll be going to 1, which is a single element array. At 1, you see that the element is not equal to 3, and you have run out of array. So the insertion point is here. Yeah, you should insert it over here at index 0. If 3 occurred, it would have been here. So fine. The question here is that should you include this value? This is your insertion point, right? So should you include this value 1? And the answer to that is no. You shouldn't, because your insertion point has a value of 1, which is less than your leftmost index 3. So it's outside your range basically. So you shouldn't include this value. Fine. So we are going to be taking all elements from after 1, after the occurrence of 2 at index 1. So 4 and 8 up to what point? 9. So when does 2 occur at index 9 or before it? That's the point that we want, right? So again do a binary search with key equal to 9 this time. Come to the center element. 4 is less than 9. So kill these guys. Right, 1 to 4 is killed. You come to this index, you see that 8 is less than 9, but you have run out of array. So this is your insertion point. And is 8 greater than 9 or less than 9? It's less than 9, and your rightmost index is 9. So it's within the range that you like. Therefore, you should include this. Alright, you should include this and everything before it. So your answer becomes what you included 8, 1 plus whatever your range of 2 indexes are, which is size of them is just 1. So 1 plus 1, which is 2. Okay, this is how you find the number of elements of size 2 in the array B using binary search. Okay, not bad. Finally, let's quickly go through the time complexity requirement. You have log n each time you are trying to find the number of k's which occur in your range. So log n to find the leftmost and log n to find the rightmost. So that is 2 log n. What else? Well, you find the leftmost block also. So that takes log n in the worst case. It's an addition to this. Is there anything else? No. So nothing else. Apart from the pre-processing which comes in at order n cost. So that's fine. So order n plus for every query, you have q into log n as the time complexity. So this order n is not required. We can, in fact, to actually read in the input, you need order n. So what's so great in having this complexity? But yeah, to be accurate, this is the complexity requirement of the algorithm. And this is easily going to clear the time limit. In fact, if you have q root n time complexity, that's also enough. You could have used the Mohs algorithm or square root decomposition. So that's it for the stable market problem. If you have solutions which are using the Mohs or segment trees or square root decomposition, then please feel free to contribute. If you have binary search, please feel free to contribute even then. But I'll be working on that myself in case a solution doesn't come along. Also, if you have any doubts or queries, of course, that's the more important thing, then please feel free to comment down and I'll be sharing relevant links and code in the description below. So until next time, see you.